Hello students, welcome back. We just went through the first half of the general solution theorem. Given homogeneous linear ODE of order n, there exist n linearly independent solutions, y1, y2, y3, and so on, all the way over to yn. That's what we proved. And what we didn't prove yet is all the solutions can be written as a linear combination of those y1 through yn. The student with some linear algebra background will understand this way. Linearly independent, we got it. And then they generate the solution space. All right, they form basis. But if you don't know what basis is, if you don't know what generating means, never mind about that. We don't need all those concepts of linear algebra. Linear independence, of course, we need it, and then we established it. And as for all solutions can be written as a linear combination of y1 through yn, let us postpone that proof, and then let's do an example problem first. Let's go to this example problem, Cauchy-Euler equation. Cauchy-Euler equation is an equation of this form, a homogeneous linear ODE with t squared y double prime, t to the first power y prime, 0 power and y. Okay, second derivative is paired with second power, first derivative is paired with first power, and 0th derivative, or the original, is paired with 0th power. In general, it goes like this. Nth derivative is paired with t to the nth power, n minus first derivative times t to the n minus first power, and so on. That's a little bit more general setting, but let's not go that deep. How to solve it? Well, I want to make sure that we're going to be using this general solution theorem here. So instead of going through this change of variable method, which actually goes via the Laplace transform, let's go to the substitution method. Substitution method is down here. Sorry about that. Instead of going up, I should have come down. The substitution method, let's do this one first. Normally, this is not very good because it has a lot of holes. But as a matter of fact, this theorem, as a matter of fact, filled out all the holes. So how does it work? Take the substitution t to the s power and then plug it in. So t to the s power, and y prime is s times t to the s minus 1 power, while y double prime is that. Okay, and then plug those into this equation, original ODE. So this y double prime, which I'm highlighting in red, is equal to this, and this y prime, which I'm highlighting in blue, is this, so it goes over here, and then y is just t to the s power, so we get that, and then second power here kills off this minus 2, first power here kills off this minus 1, and what happens here? T to the s power is common. And t to the s power times this thing is equal to 0, and this thing over here is actually a quadratic equation. We end up with a characteristic equation of the Euler equation, Cauchy-Euler equation. Let's go to an example problem. Okay, here's a problem, and let's solve it. T to the s power. Why is t to the s power, all right? y prime is equal to s times t to the s minus first power. Y double prime is s minus 1 t to the s minus 2 power. So far pretty clear. And then as before, let me do some highlighting. Okay, and then here's the original equation. And then let's see, that's gonna be replaced into this y double prime, and that's gonna go to y prime. And then t to the s power is gonna go to y. So this original equation became this because of this substitution. Y is t to the s power. Okay? And then this t to the second power minus 2 cancel each other out. First power, this minus 1 cancel each other out. So t to the s power is common. And then what's left is s minus 1. No, excuse me. 2 minus 5s plus 3. Looks like this is what I'm getting. Did I do this right? So all the t to the s power factored out. And then let's work out the inside a little bit further. Let's see, what do we have? 2s squared minus 2s. Did I do this right? After substituting. Let's see. 2s squared, this minus 7s. Okay. Going well. Let's factor this. What do we have? We have 2s plus 1, no, minus 1, s minus 3. Did I factor correctly? 2 times 3, minus 6, minus 7, okay, that's correct. I guess that's right. So as a conclusion, t to the s power is equal to 0, or 2s minus 1 is equal to 0. So s is 1/2. Or s minus 3 is equal to 0, so you get s is equal to 3. Does it make sense? The only non-trivial step is to make this educated guess, t to the s power, and the plugging in. First derivative, second derivative, and then substituted those into original equation, and after that just algebraic manipulation. Let's see, we assumed y is t to the s power, and we have those s values. So what do you get? Y is t to the s power, but s is 1/2. Here's one solution. Y2 is t to the s power, but s value is 3. So there's another solution. Therefore, the general solution can be written as C1 Y1 plus C2 Y2. So we did get the general solution. Let's go back here. The linearly independent solutions exist, y1 through yn. this is second order, so our aim is to find two linearly independent solutions. They must exist, somehow you can find it. By this substitution, we got two. 1/2 power, third power. We did get the linearly independent solutions. Clearly, you can see these are not collinear. And let's go back to that general solution theorem. Once you find those linearly independent solutions, put them into linear combination. That is the general solution, which I just did here. So that is the general solution. As a matter of fact, there's one more solution here, singular solution. Y is t to the s power. That's the substitution, wasn't it? And that being constantly equal to 0. Oops, wrong place. Coming from this actually, which I'm highlighting in different color. I ran out of color. Let's use purple. Okay, these two came from this substitution method and eventually from this characteristic equation. But this part of the characteristic equation, I have 1/2 and 3, this general solution, but another one here, t to the s power is constantly equal to 0. Y is t to the s power, so y is equal to 0, constantly equal to 0. That's another solution. So that's how you can solve this kind of equation, Cauchy-Euler equation. You can do some educated guess and substitution and then work those out using the substitution method. And substitution method usually has a lot of holes, theoretically speaking, because you're not exhausting all the possibilities. But come to this general solution theorem. Those linearly independent solutions exist, so we are just trying to find those. But once you find those, then their linear combination is the general solution you're looking for. So by this theorem, this method is actually valid. That's how powerful this theorem is. It justifies pretty much everything we do. By the way, let's check. Y of t is c1 t to the 1/2 power plus c2 t to the 3rd power, right? Okay. Simplify the left-hand side of this expression, 2t squared times y double prime of t minus 5t times y prime of t plus 3y of t. Simplify this left-hand side. Am I getting 0? Yes, indeed. I checked, and this is correct general solution I checked out. By the way, what if I define y of t as constantly 0? And yes, that too is a solution. But then again, if y is constantly 0, I don't need Mathematica to check all that. The singular solution is really simple. Anyway, that's an example of a second-order linear ODE with variable coefficient, the simplest case, Cauchy-Euler equation. And the theoretical background, here, the general solution theorem. Let's see, how much time do we have? I guess we have enough time to go over some more solutions here. How about this problem here? Plug in t to the s power in there. All right, here we go. Plug in t to the s power, first derivative, second derivative, and then plug those into the original equation. That's what we get in the second line. Did I put everything correctly? Of course I did. And I'm not doing it right now. This is already preset exercise that I did, and I've checked everything, so it's correct. And then second power minus 2, first power minus 1, they all collide, and then you have T3s power that is common, so factor T3s power out. What's left is an equation of s. It's a quadratic equation, which we call the characteristic equation. And then simplify what you have. We have this, and we end up with a double root. In that case, what do? Well, it's going to get a little bit more complicated now, but in case of double root, you get one solution coming from 1/3 power. That's clear. And then if you multiply by log of t, then that's a good way to generate a linearly independent solution that corresponds to the same characteristic value. Why is an important question, but that's something I cannot answer at this moment. If you go to change a variable method, which I'm going to explain in a separate video, then the log of t will be explained. Why in the world we get the log of t? At this moment, just consider it as a formula method or whatever. Whenever you have double root, just put log of t. And what does the general solution theorem say? It doesn't matter which method you use to find linearly independent solutions. Once you find, then their linear combination is the general solution. That's what this general solution theorem says. Well, it says many other things, but that's one of them. Let's come back here. When you have double root, and then you can put log of t to find out another solution here. Why is that? You don't have to know. If you prove this, which we'll do in a separate video, then you don't have to know, because it doesn't matter which method you select. You have a solution, then that is the solution. You see, it's that powerful. This general solution theorem is that powerful. It's okay to guess, as long as you guess correctly. Theoretically, there is no hole, because I covered and I proved everything. As for the Cauchy-Euler equation, remember it. When I have a double root, log of t. Let's go to the last example here. Again, let's use substitution. Plug in T3s power, plug it in, and if you want to do it on your own, stop this playback and then do your computation. It's not going to be too difficult. Alright, and then plug those in, and then you get this middle part. Same as before, second power minus 2, first power minus 1, they all collide, and you get T3s power, so you can factor T3s power out. So what's left is going to be a quadratic equation, and then it's a complete square plus square expression. So we have complex characteristic value 2 plus 3i, 2 minus 3i. Those are the roots. So you can use those t to the t plus 3i or t to the t minus 3i expression, which is okay. I prefer it this way, to tell the truth. Or you can rewrite this in cosine and sine expression. Cosine sine of this 3, and then log of t pops out. Why do we have this log of t popping out again? I'll explain that in a separate video when we go over change of variable method. At this moment, just regard it as a formula method. Is it okay? Yes, it's okay, because in this general solution theorem, we proved it's okay. No matter what method we select, if we have a linear combination of linearly independent solution, that is the general solution. So this is perfectly legitimate. Okay, let's stop here, and we're going to talk about it and complete the change of variable method in a separate video. And then, of course, at some point we have to come back and prove that general solution theorem.